Hello everyone. Thanks to everyone for watching this video. My name is Qidang. I am an architect and engineer. Today's video is titled Polynomial Interpolation, and it is going to provide you the fundamentals of polynomial and also the work example. I am going to give you an overview of what I am covering in today's video. First at all, it is a bit of background to the topic, and then focus on the mathematics and work example before wrapping up with conclusions. Now we will study how to interpolate a dataset with a polynomial. Here is the problem description. Given a dataset with n plus 1 points, say we denote them by xi, yi as a point, where I is an index running from 0, 1, 2, all the way to n. Here we require the axes to be distinct. Now with this dataset, we want to find a polynomial of degree n. So we here write out the general form of a polynomial of degree n, which reads Pn of x equals a sub n x to the power n, a sub n minus 1 x to the power n minus 1, and all the way down to a1x plus a0, where the a's are the coefficients for the term x to the certain power. So, we want this polynomial to interpolate the dataset, meaning the graph of the polynomial must go through all the points which is given in the dataset. So, mathematically, this says the polynomial Pn evaluated at xi must give me the value yi, and this shall hold for all the i's from 0 to n, which means there are n plus 1 points. So the goal for the problem now becomes the following. We need to determine the coefficients a0, a1, an minus 1, an for the polynomial. Counting them, we see that we have exactly n plus 1 unknowns. Why shall we do this? Let's find some reasons. So, first, the motivation could be that you have a discrete dataset, possibly obtained through some experiments, and you are interested in the values between the points of this discrete dataset. Then you need to find some kind of a function that interpolates it. Second, maybe you have a function very complicated to compute for many reasons, and then you want to find an approximation for this function, and the approximated functions you use are polynomials. If the function is complicated, and the classical operations might not be able to be executed exactly or analytically, and then if you have a good approximation using polynomial, then we know computing derivatives integrations of polynomials are very easy. There will be other applications why we want to do that. Let's start with a simple example. I have a dataset with 3 points, which I listed here: x0, x1, x2, and y0, y1, y2 in the dataset. Then I need to fit in a polynomial of degree 2. So the goal of this example is to find the polynomial. Note that all these data satisfy the relation y equal to cosine half of pi times x. Now we need a polynomial of degree 2. So we can write out the general form of such as a polynomial here. a2x squared plus a1x plus a0 is my polynomial. And we have stated before that the goal now is to find the coefficient a2, a1, a0. Once they are determined, I have the polynomial. We now use the interpolating property and write out 3 equations. The above system of equations can be written in matrix vector form. This method is originally due to Vandermonde, and the coefficient matrix is thus called a Van der Waals matrix. We can solve this system, and this is the result that we will have. So A2 will be negative 3 over 4, A1 is negative 1 over 4, A0 is 1. Putting these coefficients back, we can write out the interpolation polynomial P2. Next, we will learn a way of constructing interpolation polynomials due to Lagrange. Given a dataset, in particular given the points for the x values as x0, x1, and all the way to xn. Using that information, we are going to define something called the cardinal functions, and they are denoted as functions LO, L1, and all the way to Ln. These are functions of x, and each of them is a polynomial of degree n. And the cardinal function L, where the index I is associated with the grid point xi. The main property satisfied by the cardinal functions is the following. Consider the cardinal function L with index I evaluated at the point xj, and this value shall equal to delta ij, where the delta is the so-called Kronecker delta, which is defined as following. When the index I equals to j, and this returns the value 1. Otherwise, when I is different from j, this returns value 0, and I runs from 0, 1, all the way to n through all the given points. In other words, the cardinal function number I takes value 1 at xi, and take value 0 all the other points. This is something we call a local supported feature in a discrete sense. We now look at the way of constructing these cardinal functions. Consider the function number I. So Li of x can be simply written as the product of all these terms. So the terms are x minus xj on the numerator, and xi minus xj on the denominator. And all these terms, they are multiplying with each other for j from 0 to 1, except it at the point when j equals to I, and that is excluded. The highest power for this cardinal function will be x to the power n. Therefore, this is a polynomial of degree n. Let's write out all the terms in this product form, assuming now I is some index in the middle, not the first or the last field. So this product form can be written like this. Once we have the cardinal functions, then writing out the interpolation polynomial is rather straightforward. It simply takes this form. The polynomial is a sum over all the cardinal functions, and each cardinal function is multiplied by yi, the corresponding data value associated with xi, and you add it up, I from 0 to n. This form of interpolation polynomial is called the Lagrange form. Let's consider an example. This is the same dataset as we worked on in the previous example, where we constructed the interpolation polynomial using the Van der Waals matrix. And now in this example, we want to write out the Lagrange form of the polynomial. Let's first write the grid points. So x0 is 0, x1 is 2/3, and x2 equals to 1. And for the corresponding y values, y0 is 1, y1 is 0.5, y2 is 0. Following the Lagrange form, we first must compute the cardinal functions. And for this example, we will have 3 of them, L0, L1, L2 of x. Then we can plug in these cardinal functions into the Lagrange form and write out the polynomial P2. So P2 equals to L0 times y0 plus L1 times y1 plus L2 times y2, where we have already computed the 3 cardinal functions, and y0, y1, y2 are given data. After plugging in the numbers for the data-wise and the cardinal function, after some work, you will get negative 3 over 4x squared minus 1 over 4x plus 1 if you go back to see the example 1 we had in the previous example. Using two different constructions, we end up with the same polynomial that interpolates the data. Now we can see the errors in the interpolation polynomial. We have the plot where the data set, polynomial P2, and the function cosine half of pi times x are plotted together in the same graph. It is clear to see the errors in the interpolating polynomial. If we want to reduce the error, we can increase the polynomial degree. In this case, the degree n is increased as 3. From this plot, we see that the error decreases as we increase n. From conclusions, what we learned? In numerical analysis, polynomial interpolation is the interpolation of a given dataset by the polynomial of lowest possible degree that passes through the points of the dataset. The error of interpolating polynomial decreases as increasing the polynomial degree. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.